over on the left, see, this is actually a huge floodplain for any sort of outwash that comes from the mountains. Over on our right-hand side, we've got the backside of the San Gabriels as we are heading on the 14 toward Palmdale. There was actually a 100-year flood that went through here many years ago, about 100 years ago. I think I'm pulling this from early geology classes. But if you see, there's actually houses and stuff built all along here now, which is not a great plan because anything this low-lying is going to end up in another 100-year flood being flooded. Yeah, that's where I am currently, Sand Canyon Road. All right, we are descending into Palmdale, and that means that we are about to leave the Pacific Plate and head to the North America Plate. Off on the right, you will see water reservoir. That is, my geology teacher once described that as a sag pond. I don't 100% know if that's true or not, but I'm going to go with it. It's a sag pond because that, I want to explain what a sag pond is, which is that when you get near a fault area or a fault zone, you can have the water table come up, and that theoretically is what it is over there. Closer to us, there's the Aqueduct, the California Aqueduct. We got a sign coming up for it. If you saw the movie Chinatown, that is what a big part of the plot was about. It's about the draining of the Owens Valley, which is where I'm headed today, to bring water down to Southern California. It's what completely changed the city and made LA actually an inhabitable town. It also completely destroyed the livelihoods of farmers up in the Owens Valley, so that's real cute. It was done by Mulholland, who got a long-ass road named after him, William Mulholland. I think that was his name. Sorry guys, I did no prep work on this. I'm just going off of the stuff that I remind myself of every time I do this drive. Anyway, so that's the California Aqueduct. We're going to be I'm going to be running alongside a lot of it for the day. But yeah, as I am crossing into Palmdale, we see Avenue S. Avenue S is, if you've ever taken a Geology 101 class in my dock doesn't really work. In Southern California, you have, let's see if I can do this. Okay. Well, that was a nice attempt. I'm just going to hold it here on the thing. This is the Avenue S road cut. Avenue S road cut is one of the most famous road cuts in the world, I would say, because you can see it right there. All the deformation, that is due to the San Andreas Fault, which runs right through here. So it's a zone, it's not an exact line, but we just crossed theoretically over into the North American Plate. So that's cool. Passed through Mojave, and that is kind of where the junction of the southern stretch of the Pacific Crest Trail meets the Sierra Nevada foothills and the start of the Sierra section, central section of the Pacific Crest Trail. I will periodically think that I am going to hike the Pacific Crest Trail, and that I'm prepared to do it. If I ever tweet about it, please remind me that I am soft and I am not ready to do it, no matter how much I think I can. But yeah, this also, passing into Mojave, means that we're heading from the southern stretch of Southern California kind of into the Central Valley, or not the Central Valley, but the central portion, and we're heading into some cool geology stuff that will be coming up. All right, so I guess let's talk about alluvial fans a little bit, since we're here driving through the desert and there's a lot of them. Alluvial fans, that's a really common geologic formation you're going to see in California, Southern California, especially when you're driving through the desert. Basically what happens is that you get water running out of mountains, hillsides, and it carries the sediment out, and then the sediment, as it gets out of the kind of steep, narrow craters where it's moving, you are walking along alluvial fan. What you'll see is you'll actually see the sediment size change. So in order to move something really heavy, what you need to have is a very fast. So I just passed through Mojave, and that is kind of where the junction of the southern stretch of the Pacific Crest Trail meets the Sierra Nevada foothills and the start of the Sierra section, central section of the Pacific Crest Trail. I will periodically think that I am going to hike the Pacific Crest Trail, and that I'm prepared to do it. If I ever tweet about it, please remind me that I am soft and I am not ready to do it, no matter how much I think I can. But yeah, this also central portion, and we're heading into some cool geology stuff that will be coming up. All right, so I guess let's talk about alluvial fans a little bit, since we're here driving through the desert and there's a lot of them. Alluvial fans, that's a really common geologic formation you're going to see in California, Southern California, especially when you're driving through the desert. Basically what happens is that you get water running out of mountains, hillsides, and it carries the sediment out, and then the sediment, as it gets out of the kind of steep, narrow craters where it's moving very quickly, slows down and spreads out in a fan-like fashion. Over time it builds up more and more, and then you get this very, like, it looks like if you laid a fan down flat, not a spinning fan, but like a lady's fan, down flat at the base of a mountain, kind of a, what's the word, like a half moon shape with a triangular base point, a cone shape pointing toward the mouth of the canyons. So you get those all through here, get them pretty much everywhere, and then they all connect. A really great place to see this is Death Valley, where you have huge alluvial fans that the roads in Death Valley actually run along, and then you can hike up into the canyons. As you are walking along alluvial fan, what you'll see is you'll actually see the sediment size change. So in order to move something really heavy, what you need to have is a very fast current. So to move a really big boulder, it's got to move real fast. So as you walk up a alluvial fan, you start out with really fine sediments that are able to be carried the furthest out. And then as you get closer, the sediments start to get larger and larger until you're getting close to the mouth of a canyon, and then you'll start to get those big boulders. What's kind of cool is that over time, you actually get sort of a graded pattern if you cut into an alluvial fan. I don't know exactly what's happening in front of me, but that's cool. All right, we're just gonna let that happen. So if you cut into a vertical relief of an alluvial fan, you'll actually see that pattern happening at different places as the kind of amount of like the speed of the water moving outward changes over time. I'm trying to remember, because my sedimentary geology class has been a while. I believe that the oldest part of the fan is going to have rocks, big rocks furthest out, and then the newest part of the fan is going to have the big rocks closest in. So you'll actually, if you cut like a slice of cake into the alluvial fan, the base layer will have bigger sediments than the layers on top. Could be wrong about that. If there's any geologists out there who are watching, I don't know why there would be. It's mostly baseball followers on my timeline, and this is assuming anyone's watching. Let me know if I'm right. All right, we are in Red Rock Canyon, the California State Park. It is really confusing when you're trying to look up information on it, because there's about 17 Red Rock Canyons around the country. But this is the California Red Rock Canyon. It dates back with sediments back to the Miocene, which is, like, we're dealing with mostly deposition in the Miocene starting about a little less than 20 million years ago. And it is composed of a mix of sandstones. You have some volcanic ash mixed in, and I think limestone sediments capped with, up on top, basalt. So this over on our left hand side is going to give us a really good example of that. The red layers, those are sandstones colored by iron oxidization. Then we have the white layers. I think that those are sandstones, or they might be sandstones mixed with tough volcanic ash, or they might be limestone. And then on top you've got this hard resistant layer creating a capstone, and that would be the basalt flows. Yes, we've got basalt flows because we're getting into volcanic territory. I get really excited about the volcanics in Central California because I'm a nerd. But yeah, cool thing about Red Rock State Park, in addition to it being a great place to come and stargaze, you get amazing views of the night sky. You can see the Milky Way. It's really cool. I've been here to watch the Perseids a few times. In addition to that, one of the things that we have here is actually a really abundant fossil collection of Ice Age animals, camels, plants. A lot of research has been done here that's helped our understanding of California's geology during the Ice Age, especially that period, the 20 to 5 million years ago. So that is Red Rock Canyon State Park. All right, so we're heading into the Coso volcanic field. About 1.5 million, 1 million years ago, this area was actually very volcanically active. As you can see off on the right where the dark patch is, it's about like my 1 o'clock, there's dark patch, and then there's red hills. And those are cinder cones that would have spewed out ash and lava, creating these large basaltic flows all over the place, and rhyolite, which is a different kind of lava. There's different grade, like based on the chemical content, there's different kinds of lava. You think of basalt, the black stuff that you see in Hawaii, but there's also a much lighter kind called rhyolite, and then there's a medium kind called diorite. And based on the composition of those tells us a lot about what was happening geologically at the time down within the plates. So a lot of the lava flow through here we're going to be seeing more of in the next stretch of road that we're going to travel on. And it actually gets really interesting because you start to see how California's changing geology, because it's still very active here, not just like, not volcanically obviously, but it's just like we're in an active geologic area, how that has changed and affected things over time. That wasn't as eloquent as I wanted to be, but I'm seeding the excitement for what's coming up, which is something called Fossil Falls, which is really cool and exciting, but not for the reasons that you would think. Alright, so this is not particularly thrilling, but it is one of my favorite little bits of the lava flows over here. And you can see it off on the right. It is this little gap where the hillside is still exposed, and you can see the lava flow that had gone over it. And I just really like it because it looks like you can imagine exactly how it would have looked when it was active and flowing. That you can see this little waterfall of basalt coming over the side, and then you've got the rest of it flooding down. I just think that's a really cool little glimpse into what it would have looked like when it was happening. Okay, first of all, I misidentified a form of lava earlier. I said that there was rhyolite, diorite, and basalt, but there isn't. It's rhyolite, andesite, and basalt. Andesite, name coming from the Andes Mountains. So what's cool with this little stretch here is that you see on the right just how much lava there was. Look at how thick this is. Look at how far back it is stretching from, well, you can't see how far back it's stretching, but you saw how far back it was stretching from that last video, and this is how thick it is here, several miles away. So this just gives you a sense of just how much, with the volume of material that was coming out of the volcanic field at the time. We got some weathered boulders of lava over here. It's kind of crumbling on the side. If I had a better quality camera, what you would be able to see right now is you'd be able to see that up along the top you even get a little bit of what's called columnar jointing. Columnar jointing is famously seen in Close Encounters of the Third Kind, where at the end they're at Devil's Postpile and you get that big tower that has this weird sort of column-shaped thing happening with the rocks. And that happens when you have lava that cools, and as it cools it contracts and it forms this 8-sided octagonal column. Another good place to see columnar jointing if you don't feel like going all the way to Wyoming is, wait, did I call it Devil's Tower or Devil's Postpile? I think so it's Devil's Tower in Wyoming, but a good place to see it is actually further up this road. I'm not going to get there today because I don't have time. But Devil's Postpile, which is up by Mammoth, and that's a really great example of columnar jointing that you can see here in California. I am really hungry and like an hour away still from, oh cool, look at the bird. I don't know what the bird was, so I'm gonna ask a person who would know what the bird was, what the bird is. Anyway, I am really hungry and I have to pee, and this road isn't helping, but I am also a completionist, and Fossil Falls is like my favorite place on this whole road. So we're gonna stop here so that I can show you Fossil Falls, because if you've never been here, you should go here once in your life because it's really cool and weird. All right, we're at Fossil Falls. let's talk a little bit about what Glacial Falls actually is. Ooh, another dog for Kit to be friends with. So I don't know if you can see that there's a guy down there. There is a kind of pathway that goes down through. What we're going to do is for a second, we were on the drive, we were looking back 1.5 million years ago. Now we're going to look back about 200,000. So 1.5 million years ago, lava rolls through here, lives very happily here for a long time. 20,000 years ago, we are in the Ice Age. And in the Ice Age, California looked a lot different, not only with the glaciers, but there was a lot more water here. And so we have Owens River and Owens Lake up the way. We have all sorts of water. There's a Death Valley back behind us is going to be basically a huge lake, an inland sea really, not a lake, it's a sea. So you're going to get a whole bunch of different things there, and water flowing everywhere as the glaciers melt, as they have outwash plains, all of that. So 20,000 years ago, this became a roaring waterfall. And you can see where it carves through and cuts through this, probably I'm bad at estimating heights, but let's say 30 feet of rock. I don't know. But I was hoping to have more kind of drama to this moment, but it's me and I can't. So 20,000 years ago, if you had been sitting here on the shore, you would have had this amazing, powerful waterfall flowing through, smoothing out the rocks. And I'm going to get some close-ups of some cool features that you can see here about the basalt and the way that it has been shaped by the water itself. First off, what we've got here is what we call vesicular basalt. Vesicles, basically air holes. We've got them all through here. You can see my fingers for scale. So vesicular basalt is what happens when there's a lot of gas inside of the basalt and it wants to escape. What's going on, buddy? How you doing? You having fun? No, not really? Cool. And it wants to escape, and it punctures through this molten rock as it's flowing, and as it cools, it leaves behind the air holes. So you've got lots and lots of it all through here, all these air holes. But what that also creates are really good spots for water to flow into, and when water flows into something, it then starts to erode. So you have here, this is a really good example of what's called, let's see, there we go. This is an example, as is this, of what we call a pothole. Basically, water flows over it, gets trapped if it has, it might have another rock in it, something that can smooth it out, and it eddies and just swirls in a circle and starts to carve it out. And as it carves it out, more water's flowing over, the rock is here trapped, smoothing out, and it digs it down and creates these holes. So that's how you end up with what makes this so climbable, which is these very smooth, high-polished surfaces. With lots of little pockets and footholds and fun things for you to climb on. So the other thing, I'm going to have Kit playing with the dog in the background. The other thing that happens here, though, you can see it here, that's ice. So it's really cold here. It's about 45 degrees right now. How you doing, bud? You having fun? Okay, nope, we're not going to... Hey! Yeah, I don't want them playing on the rocks. Okay, so I'm going to try this again. What we have here is ice that has formed inside of a pothole because it gets cold here. And this is going to be not in the sun. It was freezing last night. The water that got trapped in here froze. What will then happen? Ice expands. Ice will cause more cracks, cause it to erode more. So that is how this whole thing starts to, over time, erode, crack, create more cracks, and then more water flows through, and so on and so forth, until you end up with this. All right, up ahead we have what remains of Owens Lake. You can see kind of that white flat area out there. As we get closer, we'll start to see the light reflecting off of it. So Owens Lake, back during the Ice Age, there were lots of inland seas. Salt Lake City was one of them. Death Valley had an inland sea. Death Valley being actually just a point where it destroyed the livelihoods of farmers all over here. This was an agricultural community. There was a farming community here that was completely decimated from the draining of Owens Lake. And you actually see, this is where the inspiration for all the water plot line of Chinatown comes in, when those guys bring, the farmer brings the sheep into the town hall meeting. It's referencing what happened here in the 1930s to completely just drain the lake. As a result, wound up with this ghost town. What did end up happening actually was that because there was no water to keep the sediments, lake sediments are very, very fine. So lake sediments being super fine mean that they can become airborne when a strong wind picks up. We were at Fossil Falls, you heard how windy it was. Strong winds pick up through this pass all the time. What was happening was it was causing dust storms, it was causing respiratory problems. So they actually, this residents here sued, I don't know if it was. So I'm at a rest stop, and I just want to talk about this for a second. This is a payphone, and this is what we would use before we had cell phones. We would pick this up. This is mostly for McKenna, who I think is watching. We'd pick this up, and then we'd put money into this. Can you see it? There we go, that slot. And then you'd dial these buttons, and then you'd call somebody. So a little bit of, I guess, prehistoric archaeology there. All right, now you've got a really good view of what's left of Owens Lake, which is not a whole hell of a lot. Yeah, I mean, this whole thing was filled with a lake that was, like I said, deep enough to take a paddle boat from one end to the other. And now you've got, like, if you're lucky, a foot of water keeping the sediment intact. What's really funny is that I didn't film it, but we also passed or I also passed, you along with me, I guess, past a crystal geyser plant, bottling plant. So, you know, still doing the same shit, just a different century. So yeah, that sucks. All right, we are in Lone Pine, which if you are like I am and easily confused, you always mix up with Big Pine, which is where the food actually is. I'm not going to Lone Pine, I'm going to Big Pine, and every single time I forget that, and I forget that Lone Pine comes first and Big Pine comes after. This is Lone Pine. Over on the left we have the Alabama Hills, which I'm not going to show you because we're going through town. Ooh, Copper Top Barbecue, that's where we're going, 40 miles north. I'm really, really hungry because it's now an hour past what I thought I was going to get there at. So that's fun. But yeah, so we've got, let's see if I can tilt this. Over on the left are the Alabama Hills. It's not really a good angle. Hopefully I'll get a better one later. And there's also the Film History Museum. There's all sorts of things. This is the gateway to Mount Whitney, and you can also access Death Valley from a road we just passed. There's also a lot of, Manzanar should be coming up. There's a lot of things to cover on this little stretch of road. All right, we have to go real slow as we travel through town, so I'm gonna take this chance to kind of see if I can record the Alabama Hills a little bit. This is the Film Museum. They used to film Wild West movies out here, and because this was the closest you could get to the Wild West, I guess. But the Alabama Hills, see them in a lot of car commercials. You're not going to be able to get a really good view because we're going through Lone Pine right now. They are at the base of the Sierra Nevadas. They are an outcropping of granite. Sierras are also made of granite. That's really as much detail as I'm going to get into on that. But they are outcropping right at the foothill, partly because there is a fault line that runs right along it. That there's actually, if you are over by if you go into the Alabama Hills, which is a really cool place to camp, there's actually a little cemetery from where they buried the people who had died during the earthquake. I think it was like in the 1880s, and they buried the people who died at this little from the earthquake in this little town of Lone Pine when it was first settled. But yeah, Alabama Hills, really pretty, good place to go if you like to boulder. This is just the most beautiful highway in the world. It's just a fact. passing more alluvial fans on the right, and then you've got this really gorgeous mountainscape on the left. And I was completely wrong. I realized a few minutes ago about alluvial fan layouts. The way that I said that when you cut into it, it's a layer cake. If you look at it as a layer cake, I was not thinking properly, because duh, as a fan gets built up more, the angle becomes steeper, so the water will continue to move faster. So the younger layers up on top actually will be like, you'll see the boulders going further out on the younger layers because they're getting pushed further because it's steeper. So yeah, so if you're cutting into an alluvial fan, sort of like if it's a layer cake, you're going to have the older sediments are going to be finer, and they're actually going to grade upward, because as they get further and further, it's going to stretch further and further out. So the boulders will go further out as they get younger and younger. There's probably better places to get this information than from me. I would recommend Googling alluvial fan, maybe like alluvial fan structure would be a good search term, because I am not doing a very good job of explaining it. I was never super into desert desert geology. It's not easy to see because it's on the left-hand side. I think you can kind of see a guard tower there. This is Manzanar, which was an internment camp for Japanese Americans during World War II. It is located in the middle of nowhere. It is horrible. It's right now it's December, it's 55 degrees, and that's the high. So freezing temperatures in the winter. In the summer, it gets up into the hundreds. Death Valley's not super far away from here. So horrible conditions that we kept American citizens in, horrible conditions that we kept people in. I mean, regardless of citizenship or not, we took people from their homes and did this. And if you've never been, you should go. It's as important as going to something like a Holocaust museum, because the Holocaust is huge and unimaginable, but it's very, very easy to see how we did this to ourselves, to our own people, and that's something that we need to be reminded of today. This sounds so shallow and terrible, sorry, but I can't drive on this road without at least acknowledging that that's part of it, because it's all very pretty, but then you pass that. This is the Independence Courthouse. That is where they actually took Charles Manson when they finally caught him. All right, it only took an hour longer than expected, thanks to the fact that I had to do stops and decided to do this whole narration thing for narcissist purposes. But we're here. Oh no, there's no spots on this side. I have to go to the other side. But we're at Copper Top. Yay! Yay, Copper Top Barbecue. Okay, I'm gonna turn this off before I flip a U-turn. I know. You want attention and you're probably hungry, huh? How about you sit and then you can have that. Was that good? Yeah, was that good? Would you like some more? Would you like some more? Hey? Okay. Is it worth the drive now, buddy? Yeah? Was that worth it? Okay. One more piece for now. Here you go. Alright, I've eaten, so has Kit. Now Kit's smelling things and peeing on them. And the sun is setting, so let's talk about the Eastern Sierras, which I haven't really discussed yet. And specifically glacial geology. So let's see if I can zoom in a little bit. What I'm going to be talking about specifically right here is that right there. So we're in the southern part of the Eastern Sierras. there's not full on. If you go like a little bit further north from here, you'll start to really see glacial geology. You'll start to see all the hallmarks, things like moraines, which I can explain. You'll see actual U-shaped valleys, hanging valleys, a lot of the things that you would see if you drove through Yosemite. But this right here, these little U-shaped valleys and bowl-like depressions are examples of where glaciers used to sit. And my dog's pooping, so I'm going to go take care of that. So let's talk a little bit about the geology of the Sierras, just going back to like before the glaciers. So about 65, 70 million years ago, the plate situation was a lot different than it is today. Pangaea was breaking up, which Pangaea was the supercontinent, and yep, pee on that kit. So Pangaea was breaking up, and what started to happen over along this stretch of what would become of the North American plate, it started to subduct. Subducting is basically when one plate goes, I have two hands but I can't use them, so one plate goes under the other. Let's pretend that the haystack here is my other hand. So this is one plate here, and the other one goes under. And what starts to happen is as it gets down, the plate down that's down underneath starts to melt from obviously the hot mantle or hot upper crust or lower crust and mantle. At which point it starts to melt and it's super hot. Hot things rise. It starts to well up toward the crust of the plate it's riding underneath. So that subduction happens, and then hold on. Okay, so anyway, like I was saying, the magma would then rise up and it would push into the overlying crust, and then harden as it cooled, creating what's called a batholith. Prefix bath from the meaning deep, and lith meaning rock, so deep rock. Over time, through a combination of the rock being pushed upward as overlying sediments were eroded away, as well as through faulting, so uplift from faulting, the granite batholith was pushed upward, and that's what created the Sierra Nevadas. Relatively young mountain chain. I think it's 20 million. I could be wrong about that, but I think it's only been up for about 20 million years exposed. So it's a very young mountain chain. Yeah. Let's talk about why the Sierras look so different on one side to the other. So if you've ever driven up the 5 and if you've ever gone to the foothills along the 5, either Kern River or going up the eastern entrance, or going up the western entrance of Yosemite, or if you've been up to like Oroville and Sutter's Mill and all that, Grass Valley, you'll notice that it's kind of these rolling foothills. It's very gradual sort of elevation as you move upward. And then here on the right, it's really jagged, it's really severe, it's very dramatic, and it happens very suddenly, and that's because of the way that the faulting along here works. We're heading into what's called the Basin and Range, well, not heading into, on the left, going eastward, we're in the Basin and Range province, where basically large chunks of the crust are dropping downward. Simultaneously, we have faults along the side that are both lifting the rocks up, while also dropping down this chunk, like with what we're on right now, or where Death Valley is. As a result, you get this really severe, very sharp relief that defines the eastern side of the Sierras. Okay, so just drove through Lone Pine again as I'm heading back south, and one thing I neglected to mention about Lone Pine that is really genuinely very cool, you can access from Lone Pine both the highest point in the continental United States, which is Mount Whitney, and then you can also from Lone Pine access the lowest point in the United States, which would be Death Valley. And that's not a coincidence that they are located so close to one another. You have, through this area, like I was saying before, faulting happening where a chunk of the crust is being down dropped over in what we would call the Basin and Range province, which is where Death Valley is. So it's being down dropped lower, while you also have the Sierra Batholith being uplifted. See, it's the sign. That's where you turn off for Death Valley, and then back a little ways was where you turn for Mount Whitney. While the mountains are being uplifted from the both the down dropping as well as some other faults along through here, and as a result, you get this huge change in relief that you can tackle in a day if you're feeling really ambitious.